Yes, so it's time for our final session on applications, which consists of a single talk. And this is going to be given by André van SCHAIK, but actually this is a recorded talk, so I'm going to share the video.
G'day, I'm sorry I couldn't give this talk live online tonight, but it's about 4 AM here in Sydney, which is one of the main disadvantages of living in Australia. The time zones never seem to work out. This also means that I haven't seen any of the talks that have been given so far, so there might be some repetition in what I'm about to say. For those of you that don't know me, my name is André van SCHAIK. I'm the director of the International Centre for Neuromorphic Systems at Western Sydney University. Our mission is to do world-leading research on neuromorphic sensors, neuromorphic algorithms, and neuromorphic processors, and to develop applications for these. So first I wanted to talk a little bit about why I think neuromorphic engineering is such a hot topic at the moment. So to convince you that neuromorphic engineering is a hot topic, first have a look at the number of publications per year. If you search for neuromorphic in Google Scholar, you see there's an exponential growth in the number of papers over the years, and particularly in the last decade, a massive growth. Now, I think this is because the industry is searching for alternative solutions for electronics, in that it's relied heavily on Moore's law, that we can double the number of transistors every 18 months, and that's running to an end simply because we're reaching the physical limits of what's easily possible. Another reason, I think, is that we are collecting more and more data. It's doubling at the moment every 18 months, the amount of data collected, which is incredible. And a lot of the data that we collect is redundant. There is limited new information in the data. And also a lot of the data at the moment is just not being analyzed. All this data comes at an energy cost too. There's significant growth in energy use over the years, and particularly for the next 10 years, towards 2030, it's expected that we will use double the amount of energy that we use now for data collection and data processing. And the vast majority of that goes to data centers and the transmission of the data to and from these data centers. With the exponential growth and interest in neuromorphic engineering, I believe we are on what Gardner types a hype cycle, where there is, in the beginning for emerging technology, a massive growth in interest in the technology that reaches a peak as a number of promises that are made in this initial cycle are not being delivered on, which causes a dropping of interest in the field, after which it can then establish itself as a more mature technology with regular applications. Now, the risk for us is that the drop in interest will be particularly vicious because the promises for neuromorphic engineering are so high that we can drop quite low as well, and that's what I'm worried about. So neuromorphic hardware is here on the hype cycle. At the beginning, it's listed as applications to appear in 5 to 10 years. But note, this is a slide from 2017, so the first 5 years have already passed. So we should be starting to deliver applications now. So in the next few slides, I would like to talk about some of the applications we are working on. One of my favorite applications, which is one that I made myself in the early 90s, is the silicon retina that's inspired by the fly's eye and looked at a ball for Logitech's optical TrackMan marbles. The silicon retina simply looks at the ball and determines which direction the ball is turning, which then controls your cursor. This came on the market in 1994 and was the first real product for neuromorphic engineering. But end users really didn't know this was neuromorphic engineering. It was just technology in a trackball. The trackball you see at the top right is actually still available today. It still uses the same chip as the original, and this is a remarkable 28 years that this chip has now been used in Logitech trackballs. Another exciting application for neuromorphic technology that we've worked on is the two neuromorphic event-based cameras that we've sent to the International Space Station last year. This was in collaboration with the US Air Force Academy and the US Air Force. Those cameras are on the International Space Station to look at sprites, which are basically upside-down lightning that goes from the clouds to the upper atmosphere. These lightning flashes are fast, they're very bright, and this is where event-based cameras really have an edge. On the right here, you see where the Falcon Neuro module is on the outside of the International Space Station. With the camera that looks down to look at sprites, we can also observe the Earth. And here on the left, you see a still photo taken by a high-resolution camera on the International Space Station that's mounted near our sensors, and a rendering of the event stream that we have from the event-based camera on the International Space Station. This is a Davis 240 camera. The event stream provides events in continuous time. So effectively, we have to render that into an image which would look like an apple peel of the Earth, basically. It can go all the way around and around if we wanted to. Main hope for commercialization of neuromorphic technology is our AstroSight offering. These are mobile neuromorphic space observatories. Basically, as you see on the right, they're converted 20-foot shipping containers with a sliding roof and telescopes in them. And on the back of those telescopes, we have event-based cameras to look at satellites and space junk. Now, satellites are subject to various gravitational effects and also space weather, which means that an orbit for them, an orbit that predicts where they are going to be, is typically only valid for about 24 hours. This also means that every object in space has to be observed from Earth at least once a day. So traditionally, this is done with frame-based sensors. Then the exposure time of each frame is adapted to the brightness of the object. For dimmer objects, you need longer exposure times to see them. This comes at the disadvantage that if the brightness of the object suddenly changes because the sun glints off it, you end up with overexposed frames. And of course, the number of frames per second that you get, so the number of position measurements, decreases significantly. With the event-based sensors, we get a continuous stream of data from the satellites, which allows us to track their position accurately and also track how they are tumbling through space. On the right, we're tracking a satellite, the dot that's in the center of the screen there, and the stars are moving relative to the object that we're tracking. And based on that, we can identify the stars and the object that we're interested in, localize it against the stars to know exactly where it is at each point in time. In this case, this is the Cosmos 2475 satellite, which is about 25,000 kilometers from Earth. Our roadmap for neuromorphic computing is, well, we're at the left at the moment, where we have traditional sensors transmitting significant amounts of data to the cloud. This transmission and the processing in the cloud consume significant amount of power and need significant data storage. With neuromorphic sensors and some edge processing, be that with standard digital edge processing or specially designed neuromorphic processors, we can significantly reduce the amount of data that gets collected, remove redundancy in the data, so that we have to transmit less data to the data centers, thereby consuming less power and needing less storage. Finally, I also think for processing the data that we get from these neuromorphic sensors centrally, we also need to develop applications or technology for neuromorphic compute centers that can do the compute at significantly lower power. So in conclusion, well, it's actually more a call to action. I believe neuromorphic engineering has a short window to deliver on its promises. And so we should focus as a community on developing some applications of our neuromorphic technology that industry can actually sell and that people will actually use. And also we've got to make people aware that neuromorphic technology is actually delivering on promises. So we need to let people know that neuromorphic technology is being used. Finally, a little plug. We've started this year to offer the world's first Master of Neuromorphic Engineering. In this degree, we teach you about neuromorphic sensors, algorithms, processors. We're now accepting students for next year. It will be quite selective. We won't accept more than 20 students per year into this course. Thank you for your attention.
Okay, so that was the last talk of our event. No Q&A for this one because it was recorded. So I want to thank all of the speakers for providing such a clear and interactive overview of the field, the Technical Program Committee for putting this program together, and of course you for attending this event. So if you'd like to go beyond today's talks, you will find in the download section of this event's website a PDF file that contains one-page summaries of all the talks that you have seen today. And these also contain some useful references to go further.
This is the list of our strategic partners, starting with the executive ones, ARM, Edge Impulse, Qualcomm, Sentient, and we have DeepLight as a platinum sponsor, Clickertech, Platinum, Reality AI, Renaissance, Sony. Gold sponsors are Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, SenseML, ST Microelectronics, Synaptics, SynSense, we presented today. And we have several strategic, silver strategic partners here. And just at the end, if you can go to tinyML.org website, and you're going to see a lot of events happening in this fall and in the next 6 months. Again, thank you again, and we'll stay in touch.